All right, cool. So it should be good to go. Let me go ahead and rewrite what I had written on there before really quick. So this is going to be the math 181. Not exam one review. And my name is Michael, and I was leading this review session. All right, cool. So if at any point, any of you have any questions or anything like that, feel free to let me know by way of the chat window, or you can always unmute yourself and interrupt me, or also feel free to raise your hand. I'll try and keep an eye on that. So yeah, let me go ahead. Let me actually make sure I have the chat and participants up. Cool. All right. So yeah, if you guys have any questions in particular that you guys would like to go over, we might be able to get through all of them, but there might be a couple that we might not be able to get through because there are quite a few on this review sheet. But yeah, if you guys don't have any questions in particular to start off with, I'll probably just start top to bottom, starting from number 1 here. Right? Yes, cool. Oh yeah, one thing I totally forgot to mention, does this review material match up with the review material you guys have for this exam, this sheet here? Let's see, I wouldn't want to be doing the wrong sheet. I guess even if it was wrong, you'd probably still work with it, but yeah, I'd like to make sure.
Could you do one of the problems from 2?
Yes. Yeah, so this review material does match up. So it looks the same. Yeah. Okay, yeah. So I'll just assume that's yeah. Yeah, we can definitely do 2. If you have any, I don't know if you have any particular suggestions or anyone's okay. But yeah, we can definitely do
2 or 3 if you wouldn't mind, please.
yeah, we'll probably have time to do both. So why don't we do both 2 and 3? So let me write down, so 2 and then 2. So that is, we want to determine the vertical and horizontal asymptotes. And our function here is f of x is root 1 plus 16x squared, all divided by 6 minus x. We want to find horizontal asymptotes and vertical asymptotes. All right, cool. With that in mind, I'm going to switch over to here, so it's a little easier to see. And all right, so let's look at this. All right, so first off, the first question, I think it's probably going to be a little easier to find the vertical asymptotes. How could you find the vertical asymptotes for this function here?
Is that where you set the denominator equal to 0?
Yeah, exactly. Yeah, so we'll take this denominator here, set it equal to 0. And we get x equals 6, right? Adding x to both sides, or you could subtract 6 and divide by -1. And yeah, so that means that our vertical asymptote is just going to be at x equals 6. So we're just going to have one vertical asymptote at x equals 6. And it makes sense because if you think about it, if we plug in 6 into this function, we're going to have problems with our domain, the denominator, where we'll be dividing by 0. So yeah, that looks good. So that's the vertical asymptote, not too bad. Now the bit more difficult part is the horizontal asymptote. So for that part, there's a couple different ways you can do it. There is like a way you can do it in like pre-cal where you kind of compare coefficients, or there's also a way of doing it with limits. Do you guys have any preference on which way we could use here? Or no, maybe you guys have a different way that you could do it. All right. Yeah, I'm gonna take silence is no preference. I think it's kind of good to practice with limits, and it's good to build an intuition. So with horizontal asymptotes, right? If you have like say a graph, and you have some graph coming down like this, and say we had a horizontal asymptote at y equals 0. We can see here that as we get really big values of x, we're going to be approaching this asymptote, this 0. So basically the limit as x gets really big, or as x approaches infinity in this case, is going to be our horizontal asymptote. So to find our horizontal asymptote for this case, what we could do is we could take the limit as x approaches infinity of our function here. Square root 1 plus 16x squared, all divided by 6 minus x, like that. Yeah, so then from here, we're going to evaluate this limit. So there's a couple different ways of evaluating these. So you can either compare the coefficients on the highest power terms in the numerator and denominator, or another trick you can do is you can multiply, or I guess not multiply, you can divide both the numerator and the denominator by the highest power. So in this case, it's a little bit weird because we have a square root. There's some algebraic manipulation we can do to make it work out nice. So what we can do is we can notice the highest power in our denominator is just x to the power 1. That's just a first power x. So what we're going to do is take our numerator and denominator, multiply it by 1 over x and 1 over x. And this is going to be equal to, so I'll have the limit as x approaches infinity of, and if we look at our numerator here, it's not going to be too easy to simplify this as is. So what I'm going to do is underneath the square root, I'm going to factor out a x squared. Even though it looks like we can't factor out an x squared, we actually can. We'll just be left with a fraction afterwards. So we'll have the square root of, so I'll factor out my x squared over here. And then the first term, it'll be 1 over x squared plus, and then we'll just have 16 left over. And then just multiply by 1 over x. And in the denominator, if I bring this 1 over x in to both terms, I'll end up with 6 over x minus 1. All right, and then from here, what we can do is to simplify this square root. We notice that we have something being multiplied. And when you have two things being multiplied underneath the square root, you can bring the square root to both of them. So this will simplify to the limit as x approaches infinity of square root of x squared times root 1 over x squared plus 16. This is still times 1 over x, all divided by 6 over x minus 1. All right, and then from here we can see, well, this first term, this root x squared, the root and the squared are going to cancel out, and we'll just be left with x. And then over here we have x and x. So x divided by x, that's just going to be 1. So all these are going to cancel. So we'll just be left with a limit as x approaches infinity of root 1 over x squared plus 16 divided by 6 over x minus 1. And the nice thing about this is that once you do all the simplification, now we can plug in infinity or really big numbers. And if we plug in really big numbers for x when it's in the denominator, like when you have some constant divided by x in the denominator and x is going to infinity, that's just going to go to 0. So this term goes to 0, and this term goes to 0. So we're just left with root 16 over -1. And with this root 16, we have to be a little bit careful. We can't forget to include the plus minus out front. When we take this, like, well, I guess technically you wouldn't include it until after you evaluate it. We'd say this is equal to plus or minus 4 divided by -1. And the -1 isn't really going to do anything. It's just going to flip the positive to negative and the negative to positive. So we'll still just have plus or minus 4 at the end. And so these should be the y values for our horizontal asymptotes. So our horizontal asymptote should be y equals 4 and y equals -4, like that. Yeah, so that one's a bit more involved. There's probably like a little bit of a simpler way you could have evaluated this one. This is kind of the more rigorous algebra way. But yeah, any questions on this one before we move on to the next one in this section?
No.
Cool. All right, let's go ahead. Let me make more space here. So number 3. So let's switch back to the review sheet. So not actually, yeah, it's Roman numeral 3. Let me go ahead and fix that really quick. So it's going to be I like that. All right, so that one, it's going to be f of x is equal to 2x squared plus x minus 2 divided by x squared plus x minus 2. All right. So now from here, again, we're looking for the horizontal and vertical asymptotes. So for our vertical asymptotes, we're going to do the exact same thing as in number 2, where we have x squared plus x minus 2 is equal to 0. And then we're going to need to factor this. Could someone factor this for me? What is this factor to? The x squared plus x minus 2. X plus 1, x minus 1, close. If we had an x plus 1, x minus 1, that corresponds to, what is that, x squared minus 1? That's a difference of squares. In this case, if we were to factor this, like pick your favorite method, I think pretty commonly people use x method, but there's a million different ways you can factor something. We say, okay, well, we want to add the 1 and we want to multiply to get -2. And we take this coefficient and we want to multiply 2 numbers to get -2 and add to get 1. And 2 numbers that accomplish that are going to be +2 and -1. So our factorization should be x minus 2, or no, not x minus 2, x plus 2 and x minus 1. Yeah, so that should be the factorization for this first one. I mean, there's definitely a couple other ways you could do it. You could have even guessed like, oh, well, if x is equal to 1, then we have 1 squared plus 1 minus 2, and that is 0. So we know 1's a root, and yeah, all that. All right, so I'm going to go ahead and get rid of that x really quick so we can finish solving this. Now we're just going to break this up and solve each individually. So we'll have x plus 2 equals 0, which means that x is going to be minus 2. And then we'll have x minus 1 is equal to 0. So x should be 1. So our vertical asymptote should be x equals 1 and x equals -2, like that. All right, any questions on this one before we move on to, any questions on the vertical asymptotes before we move on to the horizontal asymptotes?
No.
Perfect, all right. So horizontal asymptotes, there is a trick from pre-cal where you can kind of memorize if the degree of the top and bottom polynomial, like if we have 2 polynomials, and the degrees of the top and bottom are the same, then to find the horizontal asymptotes, all we have to do is compare these coefficients. the coefficients, I guess there's technically a 1 here, the coefficients on the highest power of x, and that's going to give us a horizontal asymptote. So in this case, it'd be y is equal to 2 over 1, which is just 2. So our horizontal asymptote should just be y equals 2. The other way you could do it like we did it in the other problem where we took the limit as x approaches infinity and we did all this math. In this case, you would multiply top and bottom by 1 over x squared. But you would find that that limit is also equal to 2, so you should get the same answer. So yeah, any questions on this one, or would you guys like me to do the limit before we move on to the next one?
You can move on. I'm good.
All right, sounds good. I'm going to go ahead and clear these problems, and we can move on to another one. Let me go ahead and go over here. All right, so how do you guys feel about number 1? You guys feel pretty good about that one?
Yeah, I feel pretty
I'm
good.
comfortable with it.
Cool. All right, so we'll probably move into number 3. So is there any problems in particular from number 3 that you'd like to go over? Or yeah, we could even just go top to bottom if you'd like.
Could we look at 8?
Yeah. Oh my gosh, can't do Roman numerals. This is 8, right?
Yep.
Cool. All right, I think I might have enough room to just do it on here. So it wants us to evaluate the limit as x approaches 6 of x squared plus 3x over x squared minus 3x minus 18, like this. I'll put this in parentheses. All right, so for these, when we have these polynomials in the numerator denominator, they're a little more complex. Typically, the first step that I like to do is factoring. So if we factor the numerator, we see both terms have an x that we can pull out. So this is going to be equal to, so if we pull an x out of the numerator, we'll have x times x plus 3, like this. And then in the denominator, we just have another quadratic. Let's see. I was going to do the quadratic formula to kind of spice up the methods, but I'm too lazy for that. I think I'm just going to go X method, unless you guys like to see another method. So we want two numbers that add to 3, multiply to negative 18. And I think two numbers that will accomplish that is going to be negative 6 and 3, I believe. So we'll have, what is that, x minus 6 and then x plus 3. That. Right, and then so we can go ahead and cancel out these x plus 3s here, and we'll just be left with the limit as x approaches 6 of x over x minus 6. All right. And then from here, so now we need to figure out, okay, so what's going to be the sort of, I guess, end behavior of this limit? Because it's not really that easy just to plug in 6, because if we plug in 6, we do get 0. We get it'll be 6 over 0. So we know we're going to be dealing with an infinite limit, right? It's going to be some sort of infinity, but I don't really know yet if it's going to be plus or minus infinity. So to check whether it's going to be plus or minus infinity, or even whether it's going to exist, let's look at the left and right limits. Let's look at the limit as x approaches 6 from the right, and then we'll look at the limit as x approaches 6 from the left. So what's going to be the limit as x approaches 6 from the right of x over x minus 6? Any ideas? No? Okay. Oh yeah, no worries. Yeah. So when these elements can look kind of intimidating at first, but the way I like to think about it when you're approaching something from the right or from the left, it means that we're plugging in values that are really close to 6, but that are slightly greater than 6. So like, for example, let's say 6.00001, right? Or add a bunch more zeros before the 1 too, if you'd like. But the thing is that whatever we plug in, it's always going to be slightly tiny bit greater than 6, right? So this denominator is going to be positive because we're plugging in values from the right side of 6 greater than 6. So we'll have 6 over 0, but that's going to give us the positive infinity, right? Because we're plugging in values that are slightly greater than 6. And then if we look at it from the left, x approaches 6 from the left, x over x minus 6, we're going to be plugging in values that are slightly less than 6, right? So say 5.99999, yada, yada, yada. And here we'll notice that the values are going to be slightly less than 6, so our denominator is actually going to be negative this time. So we'll get negative infinity instead. And here, we notice this is definitely something really important. Whenever, if you have a limit in this sense, and if you take the limit as it approaches from the right and from the left, and if these two values do not agree, in this case, we know minus infinity is not equal to plus infinity, we know that the overall limit as x approaches 6 of x over x minus 6 does not exist because the limits from the left and the right both do not exist. Yeah, so let's see, any questions on that one? Hopefully I didn't mess it up.
Nope, I'm good.
Cool. All right, is there any other problems in particular for number 3 you guys would like to go over?
I'm all right.
All right. I had some interesting ones. I think like number 7, you had to use the squeeze theorem. There were some ones where you had to use do natural log, but yeah. If you guys are feeling good on that, we'll probably go ahead and move on to number 4 for definition of derivative. And also, if I move on too fast and there was a question that I missed that you guys let me do, feel free to let me know and I can always backtrack. So is there any ones in particular you guys would like to go over from 4 between these 3?
Can we do 2 and 3?
Sounds good. Yeah, well, let's do 2 and 3. So number 4 and 2. All right, so we'll start out with 2. F of x is equal to root x plus 2. All right, now we'll move on. I will move over to the whiteboard here. And let's go ahead and erase that underline. All right, so first thing we know is what the definition of the derivative actually is. So the definition of derivative states we're going to have dy dx, or if you want to use the, I think this is Leibniz and this is the, I think this might be Newtonian notation, I forget. This is equal to the limit as h approaches 0 of f of x plus h minus f of x, all divided by h, like this. Yeah, there is the other definition with, like, I think it's like f of x minus f of a over x minus a, but this is typically a bit more useful for finding derivatives of just standard functions with the definition. All right. So now from here, it's just a matter of plug and chug and some algebra. So let's go ahead and plug in. So we have the limit as h approaches 0. So f of x plus h, all we're going to do is wherever we see an x in our f of x, we're going to put in x plus h instead. So we'll take the square root of x plus h plus 2. And this is minus, and then f of x is still f of x, just a normal f of x, root x plus 2. And this is still all over h. And here, you may be tempted to just plug right in, but you'll find out if we plug in 0 for h, then we'll just get, let's see, root x plus 0 plus 2 minus root x plus 2. These are going to cancel, so we'll just get 0, and then in the denominator, we had 0. So we have 0 over 0, and this is a indeterminate form. So we actually have to do some more work to determine what this limit's going to be. So do you guys have any ideas on how we could simplify this to make it a bit more easier to evaluate? A bit easier? I can't grammar.
Do you multiply by the conjugate?
Yeah, that's always, whenever you see some square roots, multiplying by the conjugate is typically going to be a good idea because it'll cancel out some of those roots and could simplify things quite nicely. So let's multiply by the conjugate. So all we're going to do is we're going to take our numerator here, and instead of a minus sign in between our two radicals, we're going to put a plus sign. So we'll multiply by x plus h plus 2 plus root x plus 2. And then we can't just multiply this, we also have to divide by it, or else we change everything. So we'll divide by it as well. So now we get the limit as h approaches 0. So for the numerator, if we kind of look at flowing this out, we'll have, so multiplying these two terms, it's just going to be the same term squared, and the square root's going to cancel out. So we'll just be left with x plus h plus 2. This is square root and then squared. So these will cancel out. And then if we look at the middle terms are just going to be, it'll be root x plus h plus 2. So this term times this term, but then we have minus this term times this term. So those middle terms are going to cancel out. So I'm not even going to bother writing them. And then our last term is going to be just this root x plus 2 times root x plus 2 with the minus sign out front. So we'll have minus root x plus 2 squared, and this is going to cancel out. And in our denominator, we have h times root x plus h plus 2. Oh my goodness, cannot write. Plus 2, there we go, plus root x plus 2. And then this is going to simplify to, so I cancel out the square root, I'm going to distribute this negative sign to our x and our 2. So I'll have the limit as h approaches 0 of, let's see, x plus h plus 2 minus x minus 2, all divided by h times root x plus h plus 2 plus root x plus 2 still. Now see, this actually simplifies really nicely because in our numerator, we have x minus x, those cancel. We have 2 minus 2, those also cancel. So we're just left with the h, but we also have an h in the denominator, so we can cancel these out. And the reason we can cancel these out, we don't have to worry about dividing by 0, is because with the limit, we're only approaching 0. We're taking the limit as h gets really close to 0, not quite h equals 0. So we don't have to worry about domain issues there. So now we can actually, we're just left with the limit as h approaches 0 of 1 over root x plus h plus 2 plus root x plus 2. And now finally, we can just plug in. So let's plug in a 0 for this last h here. So we'll just be left with 1 over root x plus 2 plus root x plus 2, which is just 1 over 2 root x plus 2. Like that. So yeah, hopefully I didn't make any arithmetic mistakes there. But yeah, any questions on this one before we move on to number 3?
No, but could you leave it up for one more second?
Yeah, of course. Yeah, I'll leave it up while I'm writing down number 3. Yeah, also sorry about that if I cleared before you wrote something down. I'll make sure to give you a little more time next time. But yeah, all right. So number 3, that gives us f of x is 1 over x. So yeah.
All right, you're good. Thank you.
Cool. You're welcome. All right. So number 3, we have f of x is equal to 1 over x. So what we're going to do is we're just going to plug into this formula again. We'll just have the limit as h approaches 0 of f of x plus h, like we did before, wherever we see an x, put x plus h, 1 over x plus h, minus 1 over x, all divided by h. All right, now there's a couple different ways that you can simplify this. The first thing that comes to mind is I really don't like dealing with these fractions in the numerator. So the first thing that comes to mind for me is that let's just multiply every term in the numerator and the denominator by both these denominators. So multiply top and bottom by x times x plus h. Just get rid of all the fractions. Well, I guess not all the fractions, just get rid of the fractions in the numerator, the nested fractions. So if we do this, we'll be left with the limit as h approaches 0. So distributing this to the first term, we'll see that our x plus h term is going to cancel out. So we'll just have x. And then distributing this to our second term, we'll see that the x's cancel out, and we'll just be left with minus and then x plus h. And then in our denominator, we have h times x plus h like that. Yeah, this is one way of going about it. I think you can also make a common denominator in the numerator and go about it like that. But yeah, whichever way you feel more comfortable with. So now from here, we can distribute this negative in, and we'll see that our x's cancel because we have x minus x. And then, so we'll just be left with, this is the limit as h approaches 0 of, we'll have minus h divided by h times x. Oh my goodness, why are my x's alphas today? Sorry about that. X plus h. And again, our h's cancel. Typically with these definition derivative problems, the h's are like the one h is going to cancel almost all the time. And yeah, then from here, this is equal to the limit as h approaches 0 of 1 over x times x plus h. Plug in 0 for this last h down here. Oh, I forgot my negative sign. We'll just be left with minus 1 over x times x, which is minus 1 over x squared, just like that. All right, so I went through that one pretty quick. Any questions on number 4.3?
Nope.
All right, cool. I'll leave it up for a little bit longer, and then we can move on to a different one. All right, so is there any ones in particular from 5, 6, or 7 that you guys would like to go over?
We're still looking at the work from the last problem.
Oh yeah, cool.
Could you pull up the problems list again?
Yes, of course. Sorry about that. Yeah, is it okay? And also, is it okay if I clear this, or yeah, do you need some more time?
Yeah, clear.
Okay. All right, let me go ahead and clear this. All right, cool. Here we go. All right, so that's 5 and 6, and then 7. It gives us the graph of some functions, and it wants us to sketch the derivatives.
Can you please go over 5?
Yeah, of course.
Yeah, 5, please.
All right. So let's look at 5. I think I might be able to fit 5 down here. So 5, we know that f prime of 5 is 2. And the curve we're given is y is equal to x squared over 6 plus x over 3. And we want to find the equation of the tangent line at x equals 5. So we know the slope at x equals 5 is 2. No problem. So we need to use this information along with this given value of x equals 5 to get the tangent line. So do you guys have any ideas on how we could do that? That's a little better. Yeah. So there's actually a couple ways you could do this. You could find the derivative through the definition here with this function. But what we can do is we can notice, well, we have a slope at our x value. So we have a slope. We have, I think more commonly in this sense, it's known as m. We know that m is equal to 2 at x equals 5. And we have an x value. So to find the corresponding y value at that point, all we have to do is plug in this 5. And once we have that, we'll have a point and a slope, right? And that should be enough information to give us a line. So first, let's plug in this x equals 5 into our function. So plugging in x equals 5, I guess you could technically denote it as y of 5. Be 5 squared over 6. Why did I write 26? 5 squared over 6 plus 5 over 3. And this is going to be 25 over 6 plus, and then if we multiply this fraction by 2 over 2, we get 10 over 6. So this will be 35 over 6. Oh my goodness. I cannot write today. I am sorry. There we go. All right. And then, so from here, now we're going to use one of those formulas from pre-cal for the, I think it's called point slope form, where it's y minus y1 is equal to m times x minus x1. This is one way to format it. There's definitely a couple different ways, but yeah. So in this case, x1 is going to be 5, and I guess our y of 5 or y1 is going to be 35.6. So now all we have to do is plug everything in. So we'll plug in this here, and then our 5 over here. So we'll have y minus 35.6 is equal to 2 times x minus 5. That's all right. Yeah, and I don't think they make you simplify any further than this. If you wanted to, you could distribute this 2 and then add 35.6 to both sides and combine fractions and all of that. But I think this answer is good enough in this case. All right, any questions on this one? Cool. All right. And then you guys get a chance to write everything down?
I'm good.
All right. Cool. So then I'll leave it up for just a little bit longer. So is there any ones in particular from 6 and 7 that you guys like to go over? I guess we might have time to do all of them if you guys just want to do all of them.
Could you do 7?
Yeah. Yeah, so let me do all 7. All right. Go ahead, let me clear these drawings. Also, if there is something that you don't get a chance to write down, this will be uploaded to YouTube. We'll try and get them out just a couple hours after we finish the recording. So yeah. Let me go ahead and go to number 7. All right. So for 7, it wants us to sketch f prime for the given graph of f below. So first thing for A. So for A, we're given, so we have, for the first part, we're kind of just going up with a line with a positive slope, right? And then after that, we kind of do a little bit of V. It's almost kind of like two absolute value piecewise functions. And then we come down, it's negative. And then we go up with a pretty similar slope to what we started with. So it's pretty much the same. So now when you think about how we can graph the slope. All right, let me actually use the fancy straight lines with Zoom. So get our coordinate axis, just like that. Know why it's being a little bit temperamental. Yeah, let me, there we go. All right. So now from here we see, so the slope of a line, that's just going to be a constant, right? That's just some line with some constant slope. We don't know what the slope is because we're not given values of the y-axis or anything. But we know it's just going to be some positive slope up here for a while, and it's going to be constant. And then once we hit this point right here, which is about, I don't know, here on our graph, we're going to stop there. And then we are going to come down. And then for this next part, we're just going to have a constant negative slope. So we switch all the way down to a constant negative slope down here. And then I'll have a similar thing at this point, right about here, which is about, I don't know, here on this graph, where we come up and we're positive again, like this. Yeah, I probably didn't draw this to scale, but yeah, probably good enough. And from here, the only other question is, what about these endpoints here? Should they be filled in circles or open circles? To answer that question, we need to look at the graph. And we need to look here. So here we see that we have a v, right, an absolute value of v. And here, we actually can't differentiate this. This is not differentiable because no matter how far we zoom in, it's always going to be a v. It's never going to be a distinct positive or negative slope. So it's not really increasing or decreasing. So we're going to have a hole in our graph. So wherever we see a v, we're going to have a hole. So we're going to have a hole here, 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 and here. Yeah, that was kind of a hand-wavy explanation, but hopefully it made some sense. So yeah, and then with that, I think it should be good. I don't think your professor will be too particular on exactly like how far up these lines are, as long as they're pretty close to the same. It should be okay, and we don't have to include labels here because they didn't include labels on the original graph. So yeah, it's also making sense for number 7a.
Yes.
All right. Cool. I'll go ahead and leave that one up while we move on to B. So let me go ahead and get these coordinate axes. So for B, oh shoot, that's not great. Move that down just a little bit. There we go. So we're given, let's see. So if we look here, we see that on the left side of our graph, it's flattening out, right? It's approaching, the slope's kind of approaching 0. So we know that our slope is going to start pretty close to 0. So kind of about right here, it's kind of starting this almost kind of the same as our original graph, right? And then so our slope is going to get more and more negative, it's going to get steeper, 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 steeper until about right here. Oh, did you have a question? Okay, yeah, I guess not. Yeah, and then at about, I guess maybe right about here, we're going to stop getting steeper and we're going to start getting smoother. So we're going to come down, the slope's going to get negative, big negative, and then it's going to, at around this point, it's going to start coming back towards 0 again because we're starting to flatten out again. So we're coming back towards 0. And then at 0 here, we just have a flat tangent line. So our slope is just going to be 0 there. So we're just going to cross through the origin. And then now after that, we're going to have a positive slope that's going to increase, 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 get steeper and steeper all the way until about, I don't know, this point where we're going to top out. And then we are going to slowly get smoother and smoother as the slope comes back down to 0 again, like this. So kind of a crude drawing, but this is kind of what it's supposed to look like. So yeah, any questions on 7b? Put a little arrow.
So is it just where the slope is negative, you're drawing it below the x-axis, and where it's positive, you're going above?
Yeah. Yeah, like in the first case, it's nice and simple like that because the slope's constant. But in this case, the slope actually isn't constant because it's kind of changing, right? The graph's getting a little bit steeper and less steep as we move along. So we do have to kind of represent the graph getting steeper by making it go more negative, but yeah. I don't know if it answers your question, but hopefully it does.
It does. Thank you.
You're welcome. All right. Yeah, so now we're going to go ahead and wrap up with C. So let me go ahead and get the coordinate axis. There's that. Oh, shoot, that's kind of slanted. Let's get a better one. All right. Cool. So now, I guess I should probably write, because this is F prime for B, and this is F prime for A, and this is going to be F prime for C. So for C, now we notice that our slope, so we look at coming from left to right, we see that we are increasing really fast, big increase. Right, so we're starting way up here with our slope. It's way positive. And as we cross here and then we're getting a little bit less steep and less steep up until we hit this 0 point here, this horizontal tangent line right here. So we're really positive coming down, and then right about here-ish, we're going to cross the axis. And we see that after this horizontal tangent line, this 0, where the slope's going to be 0, we switch to negative. So we're going to go negative for a little bit. But you see here, this negative slope is definitely not as steep as this original positive slope. So we're not going to go that far negative. We're just going to go a little bit. And then we see right about here, we're going to get less steep again. And we're going to come back around. And then we hit 0 at the origin again, where we have another horizontal tangent line right there. And then we're going to have similar behavior on the other side, where it's positive for a bit and then comes back down, hits 0 right here. And then from there, we see now we're going to be decreasing. We're going down at a really fast rate. So we're just going to completely fall through the floor down that way, like that. All right, so that's going to be the F prime for C. Any questions on that one?
Nope.
Perfect. All right, I'll leave that up there for just a little bit longer. We got about 10 minutes left. I can probably do maybe a couple more problems. Is there any other maybe limits you want to go over, or maybe number 6, anything like that?
I'm all right. Thank you.
Cool.
Thank you for the help. I'm gonna go.
Yeah, of course. Yeah. Good luck on your exam. Yeah, well, in that case, if no one has any more questions, I think I'll go ahead and end the review session here. Yeah, if you guys happen to have anything else come up, feel free to call into the Math Center. Good luck in your exam. Make sure to get a good night's sleep beforehand, and get a good breakfast or lunch or whatever before your exam. And yeah, have a great day.